So this set of notes, the purpose is to learn how to use statistical analysis to determine significance of your data, and when you make a claim, having confidence in that claim. And we're going to be using this throughout the entire year. So when you look at graph A versus graph B, the individual dots in these scatter plots represent the data points for some sort of independent variable, and its effect on the resulting variable, the dependent variable. And the line is like the general trend of the data. And even though they have the same general trend, as you can see here and here, which one shows less spread from the general trend, A or B? So hopefully you're thinking B shows less spread. And then which one gives more confidence to the effect of the independent variable on the dependent variable, the input on the output? Well, the less spread the individual data points are around that general trend, the more confident you can be in that general trend. If you look at A, graph A, as the independent variable is increasing, the dependent variable could be low or it could be high. It doesn't really matter what the independent variable is. The dependent variable could be anything. But if you look at B, as the independent variable increases from 100 to 200, there is some slight variation, but in general, the dependent variable increases from 0 to 275 pretty consistently. So the higher the independent variable, the higher the dependent variable. And so for graph B, you would say that as the independent variable increases, that is going to cause the dependent variable to increase. And you can say that with confidence. With graph A, you can't say that with confidence. So therefore, you would say, as the independent variable increases, that is going to lead to no effect on the dependent variable. So the independent variable increasing or decreasing has no effect on the dependent variable. So scientists, when they're collecting data, they have to collect a sample of data. They can't look at every single individual in a population, whatever it is that they're collecting, due to time, money, and feasibility. So therefore, they have to use that sample to represent the larger population. And so you can think of sample as the number of trials you're doing for a particular group. The more and more trials that you do, the more valid your data is. But again, there's always going to be some constraint with time and money and feasibility. So what you do is you look at you do your experiment multiple times, and then you average those trials together. And that's going to give you a general idea for that particular group, what the trend is. So for each group, the trials will average together to what's called the mean. But you also have to look at the spread of the data around the mean to determine kind of like this. Is the mean actually significant? Is there a trend, or is this mean meaningless? If the sample size, number of trials, was small, so you didn't really repeat the experiment many times, and then the spread around the mean was large, so each trial was completely different than the next trial, is it actually reflective of the true mean? And the answer is no. So that means that it's like bad science. There's no good data there. So to calculate the mean or average of the data, it's X with a bar over it like that is the symbol for mean. And this is what it looks like on your formula sheet. N is referring to the number of trials. Or you could say sample size for a particular group. So to put that into context, what this means, this is a data point for all of your trials, however many you do, and then you add those up and then divide by the total number of trials. So if for a particular group they're trying to look at tomato plants, They exposed tomato seeds to an artificial light source for 20 days. At the end of 20 days, the students measured the height of the tomato plants that grew from those seeds. So after 20 days, here's the heights for these 5 tomato plants. So our number of trials, or sample size, equals 5. And then this represents the individual data points, so x1 through x5. Okay, so you just do the mean equals, add those numbers up. Do that first, get some giant numerator, and then you are going to divide by n, which is the number of trials, 5. Go ahead and calculate that. Pause me. You're going to be doing lots of these in class, and it's going to get harder, so please don't not do it. Okie dokie. So we have 305 millimeters for our numerator. Divide by 5, and that is going to be equal to 61 millimeters. So hopefully you got that as well. So that's our calculated mean for this small sample. Now, when we're looking at the individual data points, are they close to the mean? That would be good. If they're far away from the mean, like 52.71, that could be due to the other factor, like maybe uncontrolled factors, like some tomato plants are watered more than others, things like that. So you want your numbers to be close together by making identical conditions within your group. So how does this apply to the general population? If the students went out and collected hundreds of samples of tomato plants as opposed to just 5 and grew them under the same conditions that they did and graph the data, they should find the center of distribution to be around 61 millimeters. So if that's their average, that's their mean. If the center of distribution here is 61 millimeters, then there would be like a bell curve. Some of the hundreds of tomato plants, some of them would be higher than 61, some of them would be lower than 61. But the amount of plants that are close to 61 is going to be much higher than the amount of plants that are like 81 or 20. There's going to be less of those. Okay, so that's called the spread of the data, or standard deviation. And that's symbolized by a lowercase s. Here's the formula for standard deviation right here. If there's not a whole lot of spread around the mean, so every data point is pretty close to 61, your bell curve is going to be more narrow, and this is going to be good. If you have a high standard deviation, a lot of data points are going to be further away from the mean, and not as many are going to be very close to that 61, and that's bad. So low standard deviation, again, is good. And that means the data points are close to the mean. There's less spread. High standard deviation is bad. And that means the mean is meaningless because the data is kind of all over the place. High spread may be indicative that the experiment is uncontrolled, and that whatever like conditions you're doing, it's not really affecting the dependent variable, and there's other factors that are affecting it as well that aren't being controlled for. So the independent variable has no effect on the dependent variable. All right, so you're going to need to know how to calculate standard deviation, and we'll do more examples in class, but it's S equals the square root of the summation of a particular trial minus the mean squared divided by the number of trials minus 1, which, by the way, the number of trials minus 1 is called the degrees of freedom. So you have to do this in a particular order. The first thing you need to do is the numerator. After you've done the numerator, then you divide that by the number of trials minus 1, which in our case would be 4. 5 minus 1 is 4. And then the last step is going to be to square root the whole thing. If you don't do it in that order, you're going to get the wrong answer. So this is the part that confuses students, that summation symbol. So basically it just means to add up, so like if I did trial 1 minus the mean and squared, I get a number. I do trial 2 minus the mean, square that, I get another number. Summation means to add those numbers together. So to write it all out, S equals square root of, for my numerator, my first trial is 65. The mean we calculated to be 61, divided by my second trial is 52. Mean is 61 squared, plus, I don't know why I said divided by, I was getting ahead of myself, so just keep doing the numerator. So 65 minus 61 is 4. 4 squared is 16, so that's what that number would be. 52 minus 61 is actually a negative number, but we don't want negative numbers in standard deviation because we're looking at how spread apart each data point is from the mean. So to counteract that, we're going to square that negative number. That's the point of squaring, because when you square a negative number, it makes a positive number. So 52 minus 61, even though it's negative, when you square that, it's going to be positive. So when you're summing these up, you're not going to be subtracting any of them because we're looking at how each data point is spread from the mean. So this is a high spread, so we need this number to be positive. Okay, so basically just disregard the negative. Okay, and then the next trial is 71, mean is 61 squared. And then we got 56 minus the mean squared, and then our last trial is 61 minus the mean squared. So this one is going to be plus 0. So if all the data points were exactly 61, the numerator would be 0. And then because 61 minus 61 is 0, plus 0, plus 0. And so since the numerator is 0, the standard deviation would be 0. And that would be like ideal conditions. And then 5 minus 1 is 4. So you do your numerator, get whatever that number is, divide it by the number of trials, and the more trials you have, the smaller your standard deviation is going to be. So you want to have as many trials as you possibly can. So if they had done 10 tomato plants instead of 5, they would be dividing by 9 here instead of 4. Those students in the example. And so that would give them a lower standard deviation, which is a good thing. So if a test asks you, how could you lower the standard deviation? Always say to increase the number of trials. And then another thing you could say is make sure that it's all under identical conditions. All the trials are. Okie dokie. So now calculate that, please. And hopefully you got, let me go to my key, unless I'm wrong, about 7.45 millimeters. Okay? So we're going to use this number right here, 7.45, and let me actually go to this graph right here. This represents the percent of your data within that bell curve. So if this is the mean of 61, 68% of the calculated data should be within one standard deviation. So 61 plus 7.45 and then minus 7.45, that would represent 68% of your data. 2 standard deviations would represent 95% of your data. So you would take 7.45 and multiply that by 2. You get like 15 or something, and so you had to add 15 and subtract 15 from 61, and that would represent 95% of your data, and so on. So that's what that is, but that's more of a statistics class thing. Okay, so we're going to use standard deviation to calculate what's called the standard error, and this one's easy. Of the mean, and that is written as SEM or SE subscript X with a bar over it. Standard error of the mean, and it takes the standard deviation and then again divides it by the square root of the number of trials. So you want this to be low as well, so having a large sample size, a large number of trials is always going to lower it. And it reflects how true the calculated mean is to the true mean of the population. How good of a representation is that 61 millimeters to all tomato plants potentially grown with that same condition? All right, so low standard error is going to increase your confidence. in the mean. You want to have a low standard error. And it's commonly given as plus or minus 2 standard errors of the mean, and that will give you a 95 confidence interval for where the true mean lies. So to put that into context, let's calculate it. So 1 standard error of the mean in our sample, our standard deviation we calculated to be 7.45, and our number of trials is 5, so we're going to divide that by the square root of 5. So I would calculate the square root of 5 first, get an answer, and then do 7.45 divided by that number, just to make sure you're doing it in the right order. And then when I got it, I got 3.3, but you write plus or minus 3.3 because it's this is how you're going to calculate what's called an error bar on your graph. So our standard error is plus or minus 3.3 for 1 standard error of the mean. If it asks you for 2 standard errors of the mean, which it'll often do, you're just going to take that number and multiply it by 2. 3.3 times 2 equals 6.6. So plus or minus 6.6. All right, so this is how an error bar graph is formed. So if we want, for example, to graph your mean with a 95% confidence interval, we would look at 2 SEMs. So if I have my tomato plant group here on the x-axis, and then their height grown in millimeters in that time frame on the y-axis. So I need to get to 61. So I make even increments. Now I'm going to go past 60 because I'm going to have to make a confidence interval. So if I have my bar for this group of tomato plants at 61, the tip of that bar, 61, represents the calculated mean from sample. Okay? And then what you do is you take 61, your calculated mean, and you're going to have to add 6.6 to it. So then that gives me 67.6. So I'm going to draw a line, a little bracket going all the way to 67.6, and that's not perfect. It looks more like 69, close to 70, but whatever. I shouldn't say whatever. And then you also have to subtract it. So 61 minus 6.6. Okay? So $54.4, or you could just do minus 6 on this. Okay, so this represents my confidence interval, or my true mean. And that's that we don't know where the true mean lies for this for tomato plants. We know that it's somewhere within this range, and we can say that with 95% confidence. In science, the general rule is that if the error bars of 2 means, so if I had another bar right here, and I'm looking at a different type of plant or in a different range of conditions, if their calculated means are different, but this range, their ranges overlap, then that means they're not significantly different from each other because their true means could actually be the same. So if they do not overlap, however, then you can say they are significantly different. So you can say with 95% confidence, because you use 2 SEMs that's derived from this, that the difference in the means is significant, and therefore you can reject the null hypothesis, which is that there's no difference between the 2 groups, no significant difference. That's always the null hypothesis, by the way. If the error bars obviously overlap, then that means their true means could be the same, and therefore you have to accept the null hypothesis, or another way of saying that is fail to reject the null hypothesis. So that's not a good thing. So you want your confidence interval to be small, So that way you avoid overlap in confidence intervals. And to make your confidence interval small, you need a small standard error, and therefore you need a small standard deviation. So therefore you need these numbers to be close together by having very identical conditions, and you want to have as many trials as possible. So that's how science works in a lab. So to see if you understand that, which graph shows a significant difference between the groups, and which data set would you have to accept or fail to reject the null hypothesis? So we'll call this group A, or graph A, and this is graph B. What do you think? So graph B shows that their calculated means are different from each other, and their error bars do not overlap, so their true means are different from each other as well. And you can say with confidence that light increases the mean number of germinated seeds over seeds being grown in the dark, which that doesn't make a whole lot of sense to me. Seeds are grown in the soil. I don't know. Okay, and then for this one right here, I don't know what we're looking at. ND versus D is our independent variable. D has a slightly higher D has a slightly higher calculated mean, but their error bars overlap, and therefore their true means are not significantly different from each other. So this one, you would say no significance, and therefore you would have to accept the null hypothesis. Here there's a significant difference, and you could say light increases number of germinated seeds. And you can say that with 95% confidence. Okay, so have these notes filled out when you come into class, and we're going to do, you're going to be doing these practice problems with your group, and I'll be coming along to help you.